Okay, in section 3.3, you are going to be very happy when we get done with this because you'll be able to breathe a sigh of relief and not have to use the limit definition anymore to find derivatives for certain functions. Okay. Still need to know how to do it, and one of the reasons why we learn it with the limit definition is to make a major emphasis on the fact that when we find the derivative that we're finding a slope. Okay, so that's why we learn it the tedious way first, because most of the stuff that once we learn these rules, okay, then the rest of it is essentially just manipulating expressions. Okay, but in the long run, what we want to be able to do with derivatives is solve problems, okay, real-life problems that involve rates of change. Okay, so it's important to recognize that when we find the derivative, what is the derivative? Why are we finding it? What is it for? Okay, what is it really telling us? Okay, so we're going to go through some rules here, and we'll start with the first type of function, essentially the simplest type of function, y equals c, some constant. And we know by picture, if we were to look at the picture of a y equals c, it would be a what kind of line? It would be a horizontal line. So therefore, in my example in this one, the derivative is always going to be 0. Because if I'm on a horizontal line, what is the slope of that horizontal line no matter where I'm at? It's 0. So the derivative of any constant is going to be 0. So that's rule number 1, if you will. Okay. All right. Then the next rule we're going to look at is what we call the power rule. And you might have asked in the past few days when I've just given you the answers to what the derivatives are for functions like I did earlier with that x plus 1 all squared. I just told you the derivative is 2x plus 2, right? Okay. That's because in my head I could use the power rule and figure out what the derivative is without having to use the limit definition. Okay. And the power rule states as follows: if we have any power function, x to the n, okay, the derivative is always n times x to the n minus 1. So whatever the power is going to be multiplied by, out in front, it's going to become a coefficient, and then the power goes down 1. So earlier, when I had, as I said, x plus 1 all squared, okay, in my mind I FOILed that and had x squared plus 2x. Okay, and what did I do with this? I made it 2x to the what? I made it 2x to the 1 less power, right? And then with 2x, what's the power on x? It's 1, so I did 1 times 2, that's 2. And if I go down a power, x to the 0 is what? Is 1. So therefore I would have 2x plus 2 would be the derivative of that function. Alright, so when using the power rule, okay, we just again have the n, whatever the power is, becomes the coefficient, and the power goes down 1. Okay. Now, a couple examples here. If I have x to the 5th, of course, the derivative of that is going to be 5x to the 4th. Okay. If I have 3x to the 5th, if there's a constant out in front, okay, what you can do is just disregard the constant for the time being. Okay, do the derivative as you would normally with the power rule, okay, and then multiply the 3 back by that constant. Okay, so the final answer for 3x to the 5th would be 15x to the 4th. Okay. Questions so far? Could we then, if we know that this is the result, could we then just think of this as, if this is 3x to the 5th, could I just take the power, multiply it by the coefficient, and then lower the power 1? That's all you're doing anyway, isn't it? Okay, so do you really have to show this intermediate step? No. Okay. All right. So when dealing with a constant multiple, we can either do it this way, as I showed, or we can just multiply. When we have an addition or subtraction, this is rule number 4. Okay, this is ultimately the constant multiple rule in your book. It's rule number 3. Okay, if we have an addition or subtraction of a bunch of different terms, okay, the sum and difference rule tells us that we can do each of those parts individually. Okay, we can just go one piece at a time, okay, and figure out the derivative. So the derivative in here, 5x to the 4th, if I start with that one, 4 times 5 is 20. Lower the power 1, gives me 20x cubed. And if I had 3 times 2, 6, lower the power 1, that becomes x squared. 6x squared, 2 times 6 is 12. Lower the power 1, that becomes x. And then negative 3x. Keep in mind, if I just look at negative 3x alone, okay, isn't that a linear term? So if I just had y equals negative 3x, what would be the slope of that? It would just be negative 3. So any linear term is just going to be the coefficient. And why is there nothing after that? What's negative 5? Okay? Negative 5 slope is 0 because negative 5 is just a constant. So anytime we have a constant in our list, the derivative of that is always going to be 0, as we discussed up top. Okay? All right. So, and just as an aside at this point, if I ask you to take this right here and use the limit definition, okay, think about what you'd have to do. First of all, you'd have to have a plus h in here. You'd have to raise that to the 4th power, so you'd have to write a plus h 4 times and start boiling. True? Then you'd have to do it with the 3rd and the 2nd and the x. Okay? You'd have a pretty long string of a's and h's, wouldn't you? Okay? It could be done. You know, it certainly can be done, but it would take a long time, wouldn't it? So luckily, we can thank Newton and Leibniz for coming up with these rules to make this a whole lot easier for us. And so from here on out, when we have a problem like that and we have to find the derivative, okay, we can just use the power rule anytime we have a polynomial function. Okay. Questions so far? All right. Now, one of the other issues that we have is, what if we have a product of two functions? How do we deal with a product of two functions? Well, if you follow me on the book, I'm on page 115 right now. Okay, the product situation you can handle in one of two ways, and really sometimes it's only one way. In this particular case, if you recognize that you have a product of two things, okay, you can do, if it's a polynomial, you could multiply it all out. You could FOIL that out and then use the power rule. Okay, so that's one option. Okay, but one thing that you can't do, notice what I did over here, it does not equal the derivative of the first one times the derivative of the second one. Because if we did it that way, if we thought, oh, well, maybe it's just the derivative of this times the derivative of this, notice what we get. We get 2x. Is that the same as what we get when we multiply it out? No. So that's why I have crosses here. This does not equal the derivative. Okay. This is the derivative. Okay. This is not. So it's not just simply a matter when we have a product of multiplying the derivative of this times the derivative of this. Okay. The power rule states as such. Okay. And I'm going to say this in words. Okay, and I would memorize it in words as opposed to in symbols. Okay, if we want d dx of uv, u and v being two functions, okay, that it's the first function times the derivative of the second function plus the second function times the derivative of the first function. Okay, and then if we get those two figures and we add them together, that is the derivative. Okay, so. And here's where I wrote in English words. I would rather memorize that than memorize those symbols. Okay, we just say, for quick terms, it's the first times the derivative of the second plus the second times the derivative of the first. So identify a first and second function, and then from there, you can go ahead and go to work. So let's take a look at what I did here for this above example. Get the example back on the screen here. Okay, so I did exactly what this said. I said first. So in mine, my first function is this x squared plus 3. So I got that here. Okay, and my 1 comes from the fact that that's the derivative of the second function. Because what's the second function? It's linear. And what's its derivative? 1. 1 plus 0. So it's got a linear and a constant. And then plus, and now I wrote the second. The second function for me is x plus 2. And then how do I get 2x? Okay. 2x is the derivative of the first. Okay, x squared's derivative is 2x, 3's derivative is 0, so I just get 2x and that's it. Now, to show that that in fact matches up with what I got above, okay, we'll go ahead and expand here, combine like terms, and notice what I got. How's that compare to the other way I did it? It's exactly the same, isn't it? Okay. Now, in the case of a binomial times a binomial, okay, we might ask, which way is better? Okay, is it better to expand it and then get an answer that way? Or is it better to use the product rule and get the answer that way? Okay, well, I guess the answer to that question is it depends on how tricky the expansion is. Fair enough? You know, which one of these is going to take you longer? Okay, in this particular case, it would probably be quicker just to use the power rule. Just multiply it out and use the power rule. Okay, but either way we do it, we'll yield the same answer. Okay. All right. Okay, I want to look at another product rule problem here. I have y equals x sine x. Okay, who remembers what we learned yesterday about the sine x's derivative? It's cosine x. Okay, so here's my product rule work for that. I did the first, which is x. times the derivative of the second. The derivative of sine is cosine, plus the second, which is sine, times the derivative of the first. Okay, so identifying my first function and my second function, okay, allowed me to do first times the derivative of the second, plus second times the derivative of the first. And so the final answer for dy dx in this case is simply x cosine x plus sine x. Questions so far? All right, and as you can imagine, based on the product rule that we just learned, when we are using what we call the quotient rule, okay, if I have a quotient of two functions, okay, it's not going to be as simple as just taking the derivative at the top and the derivative at the bottom and dividing them. Okay, it wasn't that way for multiplication, so I can't imagine that's going to be the same for division. So here is the quotient rule in Leibniz notation. Okay. And this is on page 117 if you're following with me in the book. But what I'm going to give you is this in English words because I think this is much easier to remember than the symbols. Okay, all we do to get the derivative of a quotient of two functions is take the bottom times the derivative of the top, and then minus the top times the derivative of the bottom, and that's all divided by the bottom squared. Okay, so that's what it looks like in symbols. That's how I say it in words, because I have a lot easier time remembering the rule when it's in words than in symbols. And hence, we can go forth with something like this, where we have a product of two functions. And if we set that up correctly, we're going to go again, bottom times the derivative of the top. So notice I did x times 2x. The bottom function is x, the derivative of the top function is 2x, minus, and notice I put this second part in parentheses. Very important that the whole thing gets put in parentheses so you don't mess up any signs. And what do I have in here? I have the top times the derivative of the bottom. And then on the bottom of that fraction I have the bottom squared. And what was the bottom? The bottom was x. If I square it I get x squared. Alright, and then from there it's just a matter of simplifying. I multiply the x and the 2x, and I go minus x squared minus 3 if I distribute the negative 1 into the parentheses. I can combine like terms and I can get x squared minus 3 on top, x squared on the bottom. And I also put this little notation on the left hand side because even in calculus class, okay, I've had people simplify that and then cross out the x squareds and tell me the answer here is negative 3. Okay, and that is 100% false. Okay, remember a key issue here with algebra is that you can't cross out parts of binomials. Okay, so if you cross those out and you put negative 3 as an answer, okay, would that really even make sense knowing that the graph of this is not a line? If you tell me the answer to this is negative 3, you tell me the slope is negative 3 always, that wouldn't even make sense, would it? So don't make that mistake. Okay, do not cross out x squareds just because there's one on top and one on the bottom. If these two were in a division or a multiplication with each other on top, if it was 3x squared over x squared, then yeah, you can cross out the x squareds. But not when they're part of an addition or subtraction. So make sure you cancel that mistake out of your mind and don't do it. Got it? All right. Now,